mg cosine theta. Well, wait, we have now to, before getting there, we have a tricky step to do. So now we can solve, well, let me go ahead a little bit. We can solve this equation here for the theta double dot and then get a solution for theta. And then we can plug that back in here and get a solution for lambda. So the trick is that our friend Mr. Goldstein doesn't mention is we have to write theta as theta double dot as d dt of theta dot is equal to d theta dot d theta dt, a little bit of hand waving, theta dot d theta dot d theta.
You have to write that down.
So then you can write the integral of theta dot d theta dot is equal to g over a, the integral of sine theta d theta, which is something we know how to do. And so you wind up with theta dot squared over 2 is equal to minus g over a cosine theta, and a constant of integration, which is just g over a, because you want it to be that at theta dot equals 0, at t equals 0, theta dot is equal to 0, right? Theta 0, you want this to be plus g over a, so that makes theta dot squared is equal to 0 at t equals 0, the initial conditions. So we got an expression for theta dot. So we can then back up and get m a theta dot squared minus mg cosine theta plus lambda is equal to 0, and mga sine theta minus ma squared theta double dot is equal to 0. And then from that we solve and we get lambda is equal to mg times 3 cosine theta minus 2. And this is equal to the force that's keeping it on the sphere. So when that goes to 0 is when it's going to leave, is when the sliding widget leaves the sphere. So lambda equal 0 implies that cosine theta, whereas theta is equal to cosine, arc cosine of 2/3. So this little thing that our friend Goldstein went through in like one sentence turns out to have a bit of a longer tail on it. You wouldn't easily figure it out from that.
Like every grad student textbook.
Huh?
Every grad class textbook will be that.
Oh,
Yeah.
But
at least he didn't use the magic words that it can be
it can easily be
shown.
shown. The trivial solution.
I'm not following.
Yeah,
this
the
trick.
Panofsky is insane, man.
It doesn't get any better.
But which?
He assumes it
Theta
gets
trick.
smarter as you read it.
Theta double dot equals one stuff.
Because
I
it
hope I
contains
got this
everything.
straight.
It's like
And
a,
it's like
it's like
$30
a,
a year.
it's like a
Okay,
pocket
this
booklet.
part
everything.
Yeah, it's clear.
If you know what you're doing
Clear.
at the time.
And so I can
figured we'd
write,
go through Jackson or something.
Jackson doesn't really help you. You just get good at solving problems.
Middle step is clear too. That's fine.
But you'll get Jackson problems too.
This is, what's wrong with this step?
I've nothing wrong with the first line, but when,
Oh,
just
okay.
when you integrate it now, what's going on there?
When I integrate it.
Integral theta dot d theta dot.
My writing could be. Okay, so if I've got it, so now if I have it in a form like this, then I can just do this, do the integral,
Oh, I see what's happening. Okay.
okay? So the trick is to write it in this form with those treated as independent variables, so that then is a whole time derivative, or whole derivative, not a time derivative, a whole derivative of that time dependent. Yes.
Can I ask questions? I had an opportunity to teach civil engineering at the local community college, and one of the things that we did was you did a ladder sliding off of a wall. At what angle does the ladder lose contact with the edge of the wall?
That's a,
And it ends up being that the angle is also cosine inverse of 2/3.
Yeah.
And then now, like, and that tripped me out because
is it the same thing?
it's the same angle. And I'm wondering does that mean, but the solutions to getting about that is pretty different. I'm wondering if
Well, of course.
that means that the Lagrangian
we
is the
could've-
same.
We could have written this down. In your high school class, you weren't doing it this way.
Right,
You were
right.
writing down the velocity as a function of altitude, and therefore writing down the centrifugal force against the wall, whatever.
Well, if you think of the middle of that ladder,
Center mass, yeah.
exactly, and then the other
Yeah.
things.
Oh, it would be
straining
going
to
down as a.
Because they're gonna have to go at the same rate.
Oh, see, that's always been tripping me out when I was thinking, I wonder if I ever figured that one out. But I guess that's right, yeah. Because the center of mass of the ladder is essentially the point
It's sliding.
that's sliding over a sphere.
Sounds like an Goldstein problem.
Show that this.
So this is the hard way to do something that's pretty simple. But it shows how the technique works. And the other example in the book, I think, is a little more clear. The other example in the book being the rolling hoop. Every textbook has that example.
So if we had to take into account a hoop, we would just add a moment of inertia into the
Yeah.
thing.
Okay, so can we knock off a problem or two before we